Welcome to the Regression App tutorial. This tutorial is going to be in two parts. The first part will go through a single regression dataset to show you how the app works. Generally, how do you upload data? What kind of plots can you see? Can you take out outlying data? And what kind of information you can download from the app. And after that, I'm going to go through a more complex example that is more similar to real life if you're a researcher who does assays using 96 well plates or 384 well plates. So let's just jump right into it. The first data set I'm getting off of Kaggle, where they have a salary data CSV that you can download. I'll have a link below, so if you want to follow along, you can. Essentially, there's just two columns of data. You have your years experience, where people can work from 1 to 10 years of experience, and then you have corresponding salary of each of these individuals. And the question that our app can answer is, what is the equation that best represents the relationship between the years of experience worked and the salary? So let's go to the app. So the first thing that you need to decide when you go into this app is what kind of relationship or what kind of equation do I think would best represent the relationship between the X and Y or domain and range of the data that I have. If you don't really know, you can always change later, so you can say skip. We're just going to choose linear, so I'm going to click on linear, and it takes you to the next decision that you need to make, which is, are you going to make just one regression, or are you going to do multiple? Say if you're doing a high throughput assay, this would be relevant. For this first example, we're going to do the single because there's only one data set. So we're only going to have an X and a Y column, which the X is going to be the year's experience and the Y is going to be the salary. And the app is going to spit out a regression line that has a plot, and you're going to see that we'll have the equation and R squared and a few other things that you can do as well. So let's click on single regression and come to where we actually paste our data. So I'm going to increase this so you can see better. The instructions here say copy paste from an Excel table. Of course, it can be any spreadsheet software. You should paste all the data at once. Do not try typing into this. You see there's going to be errors. It expects there to be just a paste of all the data at once. And also don't include the headers, which would be in our case the salary and the year's experience. All right. So I'm going over here. I'm going to select all the data that I'd like to copy. I'm copying this now, and I'm going to go back to the app and simply paste it in. Whoa, so I'm going to make this smaller. There, maybe that's a good size for us to see now. So what you're looking at here is a plot of all of those points that we gave, where you can see the X is the number of years worked and the Y-axis is the salary. You can see it's pretty obvious linear regression, and it's calculated the line, and this is it. Y equals 9,400 times X plus about 25,000. Gives you the R squared. If you'd like, you can zoom in and out and pan around. It really lets you break up the graph to look at any point. So I have a reset zoom if you'd like to go back to see everything. And this is just the plot. If you see here, there's a tip. Click on points to exclude them from the regression calculation. It's not necessary in this case because this is pretty nice data. But if you had a major outlier, say a point over here, you could click on it and it would exclude it from this calculation. So I'm going to do that for one point here. And you can see, did you see that it moved a bit? And so did the equation. The equation's moving, so I'm toggling this on and off. What's happening is if it's red, it's saying that this point was excluded from calculating the regression. And We don't need to do that, so I'm going to include it. Yeah, so you get this plot, and you can take out outliers. You can also get a table version of the equation that has the equation, the r squared, the a, which is this coefficient here, and the b coefficient, which is here. Some people call this, you know, y equals ax plus b. Others say y equals mx plus b. But that's what these are, and this is more useful if you have multiple equations, which if you had multiple regressions. You could copy this and paste it into Excel, you could download it, etc. Another type of data that you can get out of this is the calculation that basically if you've used that equation, this one here, for every point, what would the regression expect someone with 3 years of experience to make? 54,000. The person actually made 60, but the regression expects 54. So if we go back to that, 3 years, go back. So that's about here. Maybe this person, they made 60, but the regression line expects less than that. So you can again copy this. I just click the copy, and I'm going to show you what we get out of it. So I'm going to go new sheet, and I'm just going to paste it. And this is what you get out of it. There's an ID data set that if there's only one, you're only going to see one. You can just delete this column. You can also delete the sort. All it's going to let you do is it tells you that this was the original order of your data. It should almost always be that way, and you can just pretty safely delete it. What we have here is an X and Y. If you notice, this is the same data as you put in, but you also get this pred Y, which is for prediction of the Y based on the equation. So the actual data point for the salary for the 1.1 years was 39,343. But if you were to go off the regression, it would have been 36,187. So that's kind of in a nutshell the type of data you can get off the app for a very simple use case. Before we start the next example, I just want to point out a few more things. For example, there is a gear settings icon. You can open this, and this is how you would change the type of equation that you'd like to make a regression from. This data set, linear does a great job. However, you might want to try, I think it's pronounced LOESS, where you would need to adjust the bandwidth to look at kind of the granularity of the weights. If you want to learn more about what is LOESS, you could link to this YouTube that I did not make, but is a good explanation. Notably, there are no equations for this unique type of pseudo regression. All the other ones have equations. You could do a logarithmic, and you can see it's going to force a logarithmic on you. You have your a and your b, and your r squared. It's not that great. If you look at the plot, doesn't fit very well. You might say, hey, this looks really linear and not logarithmic. That can happen. It's not wrong. But what is actually happening is that this is just a very small part of this equation. This equation goes on, before 2 and past 10, and you would see a logarithmic type of shape come out of it, but because it forced it to this type and this small section of data, it's essentially approximating a line. So whenever you kind of see this, you should definitely just use linear if linear works, and you should only try to use the others if you know that the relationship should be either logarithmic or polynomial or exponential, or if you clearly see that it simply is. The only other special case with the polynomial is polynomials have multiple different types of orders. I have the 5 as the max because the higher order you go, and the longer the calculation takes. you should know that all of the calculations are occurring on your computer. These are not sent to another server. It's not stored anywhere. This is why this app is free. Your computer is doing all this work. So the slower your computer is, the slower this app is going to run. And so if you have a lot of data, it could take minutes. So be patient. And especially it will take much longer if you go higher order. But it's very common to do an order of 3. And you can see what happened is that you have an x to the third component and an x to the second. The 1, I guess he doesn't need to show it here. And then this is x to the 0, which is just a constant. And if you do 4, now you have an x to the 4, third and second. So you can see the computation power that is involved in these goes up a lot. This is a very small data set, so you don't see it. But generally 2, 3, and 4 should do most of your work. If you're trying to do much more than that, you're overfitting in all likelihood. So those are the settings. You can just toggle it on and off and look at your data as you wish. We're going to go back to linear because that's the most appropriate choice for this data set. And the very last thing I'd like to show you is what this is. Here we have all points, but we could also choose regression only. And you can see from the data that we added, nothing changes. So what is this about? So to show what this is capable of doing, imagine that I look at this data and I think, hey, I have 12 years of experience. I wonder what the regression equation would predict my salary should be. So I don't have the salary. I'm just wondering what it would be if I had 12 years experience, or maybe 13 or 15. Maybe should I decide to stay in this field? What you can do is simply add the x, or the year's experience in this case, without adding a y, and the app will still create the regression based on every point that has an x and a y, but it will just spit out the predicted y for every x that doesn't have one. So let's just see this in action. I'm going to copy. I'm going to go to the app again. And I'm going to start over, going back to linear, a single regression. I'm going to paste the data. And now look what we have. We have 3 green points here. And we are showing all of the points. You can see that they are on the direct line, which is the equation here. But say I only wanted to look at the regression, I could eliminate those points, so I could focus just on the regression, and I could toggle between these points. So that's what that is about. And of course, these are the expected salaries for 12, 13, and 15 years. Okay, so let's do a more complex example now. Let's imagine that we are a researcher. We work in a lab and we do experiments with cells in 96 well plates. I'm going to show you a plate layout of my experiment. So here we are. This is a spreadsheet just to show you the plate layouts of what kind of data that I'm getting so that you understand what's going on. Here we have 2 96 well plates where I have unknown amounts of cells in most of the wells that are colored in pink. Columns 1 through 10. We have some empty wells that were not used in rows G and H on both plates. And we also have a set of controls in columns 11 and 12 where the researcher has already predetermined the concentration of some cells. And they've done serial dilutions and they've put known amounts into each well here. So we have 400,000 cells, 200,000, 100,000, etc. And then in G and H, they've put 0 cells, but they're not empty. It just has media and different controls. And it's been done in replicate. So A11 is the same as A12. And these are repeated for both plates. So this is a very common setup. Even if we're not trying to look at cell concentration, maybe we're looking at antigen expression, maybe we're looking at cell cycle. Very often, researchers will have a majority of the plate with unknown measurements on experimental cells. And then in some other part of the plate, there will be a standard curve of known values. And then these plates, after the experiment is performed and everything's set up, they go into a plate reader, and you get out all this data. And you get measurements for your known concentrations, and you also get measurements for your unknown cell populations. And you use the relationship between the known concentrations and the measurements to then predict the values of the rest of the unknowns. So I hope that makes sense. Once you have the plate readout and you've elected to export it, oops, this already has the results. I hid this column. You could have results that look like this, where you have a column that says what plate the result came from. So you have plate 1 to the 96th row, and then plate 2. You have your well IDs here, which we don't need to use, but almost always you'll have an exported well ID. And then you have your measurements. And importantly, you have measurements for all of your wells, including the ones where you have a known concentration, right? So here in A11 and A12, you know that the concentration is 400,000, and these were the measurements that you got out of that. And also in G and H, if you remember, they're empty. There are no measurements here because we told the machine not to read, so they're empty. So how do we get the regression equations for the relationship between the measurement and concentration, and then get the app to help us then predict the concentration for the others? And moreover, this is what takes a lot of time in high throughput assays. How do we get the app to know which standard curves and which regression equations belong or should be used for which wells? Because in plate 1, there is an equation that will be made, but there's also a separate equation in plate 2, right? Because these are different values, and it'll be a slightly different equation. And you don't want to, use the equation from plate 1 to calculate an unknown in plate 2. I mean, maybe they were run on different days, they could have different reagents. Very often, different plates will have different standards and curves created. So what you want to do is create the input. Go back to the app here. We are going to guess that it's going to be a linear regression. And now we're going to choose multiple. And that is because we have multiple different regression equations that we want to use. And the difference in how you input it, here you've seen separate types of things, but they're not separate. This is just to help you see that there are 2 different data sets. You basically just give 3 columns instead of 2 here, where you separate which data belongs where by a dataset ID. This has 1 and a 2, but it can be anything as long as they are different from each other. This could be A and B, this could be plate 1 or plate 2. And in our case, that's what the dataset IDs are going to be, because in our data that was exported, conveniently, it already is separated that way. All of the concentrations that are known will create a regression, and it will be applied to the data that also shares the same plate ID. So we're going to use plate as the dataset ID. We're not going to use well. We're going to use X as the measurement, or measurement as the X value, and concentration as the Y value, which we're trying to predict. So let's see if I've already done this. I have. Essentially what I did is I simply copy and pasted plate, measurement, and concentration. Nothing besides that. I just left out well. And I'm going to copy all of this. Copy. Let's go to the app. I'm going to press multiple, and I'm going to paste. All right, so we have a lot of data. We have a lot of green points because we have a lot of unknowns. And I'm going to reduce the size. All right, so as you can now see, we have 2 plots to choose from. And look, we have an outlier. So you can see this r squared is 0.95. That's not that great. But if we exclude this, say for some reason we know that we accidentally added the wrong reagent, we could just confidently exclude that. And now look at our r squared. It is much better. You can see that all of the points in green, those are the experimental values mapped to what the regression line predicts them to be. So of course they're on the line, but it's kind of crowding out the actual regression data that was used. So you want to evaluate that by itself, you can just press regression only. And now you can see the data that was actually used to create the data. And this is our outlier. It looks pretty good. You can zoom in and zoom out, reset zoom, and look at plate 1. It looks like there might be an outlier, but honestly it doesn't change very much. We're not sure it's an outlier, so we can leave it there. So there's not much different in terms of the multi level that comes in terms of like looking at the plots. You just get multiple plots. And instead of one row in this table, you have multiple, so you can compare the equations. Again, you can copy and paste into Excel, you can download a workbook or a CSV, and the same with the data points. As you can see, for the values that only have the X, which is the measurement, but don't have a known concentration, there's still a predicted concentration. And interestingly, you know, for the ones with a known concentration that came from the standards, there's also what it would have been predicted. So you can kind of get a feel for how accurate these predictions are. And also you can look at your r squared. For those that don't have any X or Y, you know, obviously there's no predicted Y, but they're maintained inside the data so that when you copy it, you can copy directly in line with your original data. So I press this copy, and I'm going to go back to the data. There we are. All right, go to the top, and I am going to paste. Okay, so might look a little confusing at first, but it really is not. This is just the dataset ID that we gave it. Of course, it's the same as the plate. I like to paste everything at first because you just want to sanity check that they are aligned correctly. You didn't paste it incorrectly. So I'm going to delete that column. Are the X's the same? Yes, they are. There's nothing silly here. I'm going to delete this one because this NaN stands for not a number. You can just, you know, control find and replace with nothing if that's what you'd like. Sometimes this is useful if you're doing downstream like Python or R. But these, because they are already here, right, there's nothing new information, and I don't care about sort, just delete these. Again, they're mainly sanity checks to make sure that you've pasted them correctly. And this is pred Y, and I'm going to call this predicted concentrations. Yeah. So now you have your predicted concentrations for both of your plates. Doesn't really matter. You can delete this, you can do control find, you could leave it. But that's your data. Well, thank you for watching, and if you have questions about the code, specifically how the regressions were calculated, it's all here. This app was made completely using D3 and Harry Stevens' D3 regression libraries, which are for free use on GitHub, so thank you to them. And please, if you like this, give me a thumbs up. And if you have questions or comments, please leave a comment. Thanks.